All right, this is 6.2, all about inverse functions and relations. Okay, so algebraically, this is very straightforward, okay? Think about inverse operations, okay? So like the inverse of multiplying is dividing. So if I take, 2 times 5, I get 10. I could also just take that answer then and divide it by 5, and I would get back to the original 2. Okay, so this idea of inverse functions kind of works like that. Okay, so algebraically, this is how it will work. All right, we'll get into when this applies in a little bit. Okay, to find an equation for the inverse of the function y equals 3x minus 5, step 1 to find the inverse is we're going to switch x and y. So instead of y equals 3x minus 5, we're going to have x equals 3y minus 5. So literally just take wherever y is, put x there, take where x is and put y there. And then now we're just going to we're going to solve for y. Okay, so up here, if we have x equals 3y minus 5, we want to add 5 to both sides. X plus 5 equals 3y. And then to get y by itself, we need to divide both sides by 3. Okay, those 3's are going to cancel, and we end up with x plus 5 all over 3 equals y. Okay, another way you could see this represented would be y equals 1/3 x, or x over 3, plus 5 over 3. Remember that when we break up that numerator, we have to make sure we divide both parts by 3, but I'm fine in here if you just leave it as a big fraction over 3. However, it's easier to identify the slope and the y-intercept if we break it apart. Okay. So pause the video, give this one a try. Example 2. All right, so remember f of x is kind of like our y here. So we can just switch spots, okay? X equals negative 1/4 y minus 2. Now we want to solve for y. Okay, add 2 to both sides. We get x plus 2 equals negative 1/4 times y. And now we want to get this y by itself. So what we can do is multiply by the reciprocal. Multiply by the reciprocal. Remember, the reciprocal is just where you flip the numerator and the denominator. So the reciprocal of negative 1/4 is negative 4 over 1, or just negative 4. Negative 4. Okay, so we can multiply both sides by negative 4. And be careful with that left side. You have to make sure that you have your negative 4 times both pieces. Okay, it's a quantity, x plus 2. So we have to make sure we distribute. All right, negative 4x minus 8 equals y. And then just to be consistent, because they gave us function notation, we want to give our response in function notation. Okay, and this is how you represent an inverse function. You write f to the negative first power of x. Okay, write that instead of your y. So the inverse of f, or f inverse of x, would be negative 4x minus 8. All right, and then another thing you could be asked to do, instead of finding the inverse, you might have to verify. Okay, so here we were just finding the inverses. We were given one equation and then we had to get to the other one. And now we're going to be given 2 equations and we have to verify that they are inverses. Okay, so when we are verifying, we need to make a yes or no decision. Okay, that's our task. Something I want you to correct real quick. This and/or, scratch out the or. Okay, we have to prove that, or we have to show that both of these things are true. All right, we have to show that the composition, so f of f inverse equals x, and we want to show that f inverse of f equals x. Okay, so some tricky notation here. We're going to verify that these are inverses. So we're going to first take f of f inverse. So we're going to take 3. We're going to leave some parentheses open. Okay, because we're taking our f of x function, and now we're going to plug in our inverse into this set of parentheses. Okay, 1/3 x plus 5/3. And so what we're trying to show here is that they are inverses. So we're trying to get to a point where we are equal to x. All right, so now we're going to simplify. Distribute this 3. 3 times 1/3 just gives us x. Okay, 3 times 1/3 x. 3 times 5/3 just gives us 5. And then we still have this minus 5. And then in our next step, plus 5 minus 5 is going to cancel to give us x. Does x equal x? Yes. Okay, so that was f of f inverse. Now we need to go the other way. All right, we need to plug in f inverse of f. So we'll take 1/3, leave some space to plug in our f function. All right. This is a composition, so now we're going to distribute 1/3 times 3x gives us x. 1/3 times -5 gives us -5/3. And then we still have this plus 5/3, and we're trying to show all the way through that these equal x. Okay, next line, those 5/3 are going to cancel, so we end up with x equals x again. All right, so you may be wondering, why do we have to prove it both ways? There's a theorem in mathematics. So a lot of math can boil down to if-then statements. If this, then that. Okay, if blank, then blank. That was a big focus of geometry. All right, and so to prove something, when something's a biconditional statement, it's if and only if. So the way that this is worded in mathematics is that f and f inverse of x are inverses if and only if their compositions equal x. So because it's that if and only if situation, we're supposed to prove it both ways. Okay. More on that later if you choose to move forward in your math careers. So, question 4. Are f of x equals 4x squared and g of x equals 2 root x, are they inverses? And then we have to explain. So let's check and see. What is f of g of x? 4, and then leave some space because we're going to plug in this g function to root x. Okay, be super careful here. Our 4 is going to stay. This exponent, because we have multiplication, 2 times the square root of x, we can distribute this exponent to both pieces. Okay, so 2 is going to get squared, and then the square root of x is also going to get squared, and it becomes x. So we end up with 16x. Okay, are these inverses? No, because f of g of x equals 16x, it does not equal x. Okay, so they cannot be inverses. A couple more quick pieces of information for you. We're going to look at these graphs. What do we notice about their ordered pairs? So I'm going to pull up Desmos real quick. Let's see. Desmos real quick, and then let's plug in 3x minus 5, that's one function, and then let's plug in 1/3 x plus 5/3. Okay, so look at these functions. What do we notice about their ordered pairs? So both points, excuse me, both lines have the point 2.5, 2.5. All right, and then as we move along this steeper line, we have a point. Let's see if we can find a nice ordered pair for us. 4, 7. We have 4, 7 on this red line. And then if we move along this blue line, we're going to notice that we have a point 7, 4. Okay, 4, 7 on the red line, 7, 4 here. So the x's and y's get flipped. All right, here we have on the blue line -2, 1, which means that on the red line we should have 1, -2. 1, -2, and look at that, we do. Okay, so that's a intro to the graphs of inverse functions. So we notice that the x's and y's are swapped. Okay, so now let's look at these graphs. Do they appear to be inverses? Something else I want you to notice about this graph real quick. This is a fact of math. All right, inverse functions are reflected over the line y equals x. So let me see if I can change this color real quick. Let's see, change it to black, maybe make it dotted. All right, so if you can picture this red line, if it were reflected over this dotted line, it's going to give us its inverse. Okay, so let's see if that happens with these new functions that we're asked to consider. Okay, 4x squared, and then 2 times the square root of x. do those appear to be reflected over a dotted line? No, they don't, okay? One thing to notice is that one of these graphs is a parabola and the other is not. All right, so that's a pretty good indicator right away that they're not going to be inverses, at least in the way that they are written, because they're different shapes, okay? Looking at their ordered pairs, if we want to test that, this parabola has the point, let's see, 1, 4. And then does our black graph, does this have the point 4, 1? No, it doesn't, okay? So these are not inverses. No. And so that backs up what we found here algebraically. Okay. We'll have more on these graphs in a bit. Okay. Last thing for today. This is something that we mentioned very early in the year, one-to-one functions. All right. A function is one-to-one if each x goes to exactly 1y. All right. Regular functions, we just say that x's can't repeat. But for one-to-one functions, x's can't repeat and neither can y's, okay? So in a mapping, if this were your x and this were your y, the x has to go to exactly 1y for it to be one-to-one. All right, something can be a function without being one-to-one if it looks like this, okay? If we have an x that goes to a y, and then we have another x that goes to that same y, the y's repeat, so this would not be a one-to-one, okay? I'm not going to spend too much time with this, but it's important because a function has an inverse if and only if it is one-to-one. And we can see graphically very easily if a function is one-to-one because it's going to pass the horizontal line test. All right, this is just like the vertical line test to see if something's a function, except it's horizontal. All right, so a function is one-to-one if it passes the horizontal and the vertical line test. Okay, so graph number 4, we have a function because we see that it passes the vertical line test, right? Picture if there were a bunch of vertical lines passing through it, there would never be a spot where there's 2 points on the same line. So it's a function. Is it one-to-one though? Let's see. Does it pass the horizontal line test? No, it doesn't. If we pretend like that horizontal line was perfectly straight, pretend it didn't have a slope, all right? Maybe I could draw a better one here. There we go. There are several points where 2 ordered pairs would overlap with a horizontal line. So this is not invertible. It doesn't have an inverse because it doesn't pass the horizontal line test. Okay. Graph 5, does it pass the vertical line test? Yes. Okay, it passes the vertical line test, so we know it's a function. Does it pass the horizontal line test? So picture, maybe take your pencil or something across the screen and picture if this line were moving up. Let's see if I can give us. There we go. So picture like if this line was moving up. Notice how there's never going to be a spot where 2 ordered pairs are going to be on the same horizontal line. So yes, this function would have an inverse. What about this relation? Is it a function? So function, we see vertical line test. It passes. Okay, so it is a function. Is it one-to-one though? Does it pass the horizontal line test? Well, let's see. Let's take this this horizontal line. Now that I made it a super long squiggle, okay? Let's take this horizontal line and let's see. So let's start at the bottom. Okay, that point's fine. That point's fine. This point is fine. But when we move up, we're going to see, those 2 points are on the same horizontal line. So this would not pass the horizontal line test. It is not one-to-one. It does not have an inverse. Okay, that's all I got. See you later.